In the previous video, we learned how to model the motion of objects given their initial positions, velocities, and accelerations. And in each example, we kind of just assumed that we would know what those values were. But how do we know them? Where does motion come from? This is where we'll have to broaden our scope from kinematics to dynamics, which includes both the motion of objects and where that motion comes from. So what causes something to move? Let's say I have a simple sphere floating in space. In order to get it to move, well, I could push it, I could pull it, maybe I could attract it with gravity, but in all those cases I'm getting it to move by applying a force to the object, which can loosely be defined as a push or a pull on an object. Now forces have magnitude, which is how much you push on something, and also a direction, what way you push it in. So it makes sense to describe them with vectors. If multiple things are pushing on an object, then we find the net force by adding each of the force vectors on our object. So we've already shown that when you apply a force to an object, you'll change its velocity. But what happens if I stop applying the force? Well, its velocity wouldn't change, and it would just keep kind of drifting in the direction it was going in. With no other forces impeding its motion, it's just going to keep moving like that. This is the basis for Newton's first law of motion. A body at rest remains at rest, and a body in motion remains at constant velocity unless acted upon by a net external force. Now there's one more caveat to this, and it's that the velocity has to be measured from an inertial frame of reference. Basically, the reference frame we're measuring from has to be moving at a constant velocity. It can't be accelerating. Well, how can we know if that's true? Well, one way is to look at the acceleration of other objects. If we ever see an object accelerating without an apparent force creating that acceleration, it's called a fictitious force, and it means that our reference frame is accelerating. One example of this is a rotating reference frame. Let's say we have an observer standing on a spinning centrifuge like this. If the observer is holding a ball and lets go of it, we know that the ball will continue to move in the same direction it was going in, because its velocity doesn't change with no net external force. But from the perspective of the person on the centrifuge, it looks like the ball just accelerated downward, and so they would conclude that there's an outward force on the ball, even when there isn't. Now scientists have figured out that a lot of the stars we can see are, with an experimental error, basically inertial reference frames. Since the Earth spins relative to them, it's technically not an inertial reference frame, but it's spinning slow enough that we'll generally assume that the Earth is close enough to an inertial reference frame when we're solving for things. Newton's second law gives us a way to relate forces to acceleration. Specifically, the net external forces acting on a system are equal to the system's mass times its acceleration. Notice that we said the forces have to be external to the system. If we put a person in a box, and we let our system be both the person and the box, then even if the person is pushing on the box, we don't count that as a force because it's internal to the system. We would need something originating from outside our system, like someone outside the box pushing on it, to count it as a force. The reason we can ignore the internal forces of a system is because they end up canceling out with each other due to Newton's third law. Whenever one body exerts a force on a second body, the first body experiences a force equal in magnitude in opposite direction to the force that it exerts. In math terms, we say that the force from object A onto object B is equal and opposite to the force from object B onto object A. Thinking back to the box example, when a person pushes on the box, both the person and the box experience the same force in opposite directions. Even though the box and the person might move, they'll do so in such a way that the center mass of the system is still in the same location. So from the system's point of view, the system that includes both the box and the person hasn't moved. Let's look at an example. A box resting on a table, resting on the ground. The first system we'll look at is the box. Remember from the previous video that human-sized objects near the surface of the Earth have a near constant acceleration, g. So we can get the force of gravity by multiplying it by the box's mass, which we'll call the weight force from the Earth on the box, WEB. Now when rigid objects come into contact with each other, they have to push away from each other. Otherwise, they wouldn't be rigid, meaning they might deform or something, or they would pass through each other. We'll call the force that causes this the normal force, and it always acts perpendicular to the object's surface. So in this case, we get an upward normal force from the table onto the box. The second system is the table. It also has a weight force, but now it feels two normal forces, one from the ground and one from the table. If we combine these two systems into one big system, then the internal normal forces cancel out. Since they're no longer external to the system, we don't consider them anymore. and now we just have the two weight forces and the normal force from the ground. Now, let's put this box on an incline. The weight force from the box still points downwards, but now the normal force points at an angle like this, which means that our net force is going this way, unless we have friction. Friction acts in the direction opposite the direction the objects would slide if they were to move without friction, parallel to the surface. So in this case, it would go this way. The reason friction is there is because if you zoom in far enough to the two surfaces, you would actually see that they're pretty bumpy, and so it takes energy to get them to slide past each other because you have to move them up and down along those surfaces. Now friction is proportional to the normal force at the contact point. If you push harder down, then there's going to be more friction on the object, and the proportionality between the normal force and the friction is called the coefficient of friction. But the friction force is only going to work as hard as it needs to in order to stop the object from moving. So we say that it's actually less than or equal to the normal force times mu s, which is our concept of proportionality. The s here stands for static, and that's because if the opposing force exceeds mu s times the normal force, then static friction can't hold the object anymore, and it starts sliding. If you've ever pushed something heavy before, you might have noticed that once you get it moving, it's easier to push than if you're trying to start moving it again. And this is because at the contact point, there's actually two coefficients of friction, the static one and the kinetic one. Once you get an object moving, the amount of force needed to keep it moving drops because the kinetic coefficient of friction is lower than the static coefficient of friction. So in order to figure out which one we're working with, we'll have to solve for the normal force. In this case, it's easier to use slanted axes. Summing up the forces in the y direction, we get the normal force minus the y component of the weight force, which is equal to WEB times the cosine of theta. Remember that sine and cosine are related to the triangle, not specifically the x and y axes. So since this line is our hypotenuse, and our angle theta is right here, the line related to the y-axis is our adjacent side, which means that the y component of the weight force is related by the cosine of theta. We don't include friction in this calculation because it has no y component, right? It's only parallel to the surface. Since the block isn't accelerating in the y direction, and because the normal force can hold up the block, we can set the y acceleration equal to 0. Doing this allows us to solve for the normal force. Now when we sum up the forces in the x direction, we'll have the x component of the weight force minus friction. There's no normal force here because the normal force is perpendicular to the surface, which has no x component. We also want to make sure that the signs line up with the axes. Since the positive x direction is down the hill, the weight force is positive and the friction force is negative. Now we have to determine if the force of friction is strong enough to keep the block from sliding. We'll start by assuming that this is the case, in which case the acceleration equals 0. And this means that the static friction force must be equal to at least this quantity. So, if we compute the maximum friction force, mu static times the normal force, which we got earlier, and it's less than the x component of the weight force, then we know that the box will be sliding, and so the friction force will become mu kinetic times the normal force. Otherwise, we know that the forces have to balance because it's not moving, and the static friction force is exactly equal to WEB times the sine of theta. Another kind of force that you see a lot is the spring force. For most of classical mechanics, we assume that the force of a spring obeys Hooke's law, which says that the spring force is proportional to the length you displace it or pull it, where the spring constant is k, and this negative sign means that it's in the opposite direction. So let's say that our spring constant is 5 newtons per meter, where newtons are the SI unit for force. If I pull the string 2 meters to the right, then it's going to pull back with 10 newtons of force in the opposite direction, to the left. One last kind of force that you see a lot is the tension in ropes. Usually, we'll assume that ropes have 0 weight and that they don't break, so that they can technically hold an infinite amount of force. Let's say that we hang 2 blocks from the ceiling by ropes, block A and block B. We'll start with the forces on B. It has a weight force pointing downward, as well as a tension force on the rope from A to B, pointing upward. Since this rope can hold infinite weight, we assume that the block B isn't moving relative to block A, which means that we can set its y acceleration equal to 0 and solve for the tension force. We'll say that up is in the positive y direction, so tension is positive and the weight is negative. Now block A will also have a weight force and a tension force up from the ceiling, but it's going to have a tension force down from block B onto block A. This force right here is the Newton's third law pair to the tension force upward on block B, which means it has the same magnitude as the one we calculated earlier. In general, ropes are always going to hold tension on both sides of them. So if you have a pulley with a rope across it like this, then the forces on each side are going to have the same magnitude because the rope holds the same tension, but it might be exerted in different directions. Now if this tension force from a rope or some other force like friction is constraining the object to a circular motion, and we already know from the previous video that the centripetal acceleration is v squared over r. It follows then that the centripetal force must be equal to mass times acceleration, so it's mv squared over r. If I have a 5 kilogram block moving at 10 meters per second in a circle with a radius of 2 meters, then the force required to hold the block in is 250 newtons. Hey, some of you were asking, so I figured I would just tell you. We have a Discord now. There's a bunch of super smart people there. You should definitely come and check it out. Also, I got a Patreon set up, so if you want to see extra videos and also get early access to videos like this one, then go check it out. Oh, also, since the fall semester is just starting, there's a good chance that the upload rate is about to die, so yeah. Alright, bye.